Hi, folks. How in the world do you determine the shape of any sort of galaxy that you happen to be within? Now, that is a complicated question, and that's one of the things we're going to talk about in this section. We were talking last time about the various parts of the Milky Way galaxy. The fact that there is this central bulge and there's a halo outside. But there's also the galactic disk. The galactic disk is the large, thin, pancake-like section of the Milky Way galaxy. The disk itself contains lots of gas, lots of dust, and lots of young stars. The old stars are those globular clusters that are located on the outside plane of the Milky Way, but in the disk itself, mostly young stars. We believe our Milky Way galaxy has a galactic disk that is not flat like a pancake. It actually, I love this picture right here, because you can kind of see that it's warped, like wings on a bird as it's trying to change flight. This slight warp in the galactic disk, we believe, is due to gravitational effects of our neighboring galaxies, such as Andromeda and the Large and Small Magellanic Cloud. So our neighboring large gravitational objects are actually making our galaxy be sort of wobbly shaped, which I think is quite fabulous. Now, our galaxy has spiral arms in it. And none of the pictures you are ever going to see that look like this, that look like big spirally galaxies, are of our Milky Way galaxy. Why is that? Well, we've never actually sent a probe outside of our galaxy in order to look back and send us a snapshot. And so we are putting together a picture of what our galaxy looks like by looking at other galaxies out there and looking at the evidence that we have. So we are pretty sure that our galaxy contains a number of spiral arms. These spiral arms twirl outward, kind of like a fruit roll-up, out from, I don't know if fruit roll-ups is a good example, but out from that pinwheel center of our galaxy. We believe that we are approximately halfway out on one of the spiral arms and that we are approximately 25,000 light years away from the center. So that if this is the center of the Milky Way galaxy, you, me, and the sun and our solar system is about 25,000 light years away. So what that means is if you look towards the center of the Milky Way galaxy, you are going to see light that is 25,000 years old. So it's a long, long way from where we hang out to the center of the galaxy. How in the world do you determine shape? From the inside. Well, here's my goofy analogy, and I hope it helps make sense to you. Let's say that you are in a car, and I have a cute picture of a puppy inside of a car instead of you or me. But let's say you're in a car, and you don't know what your car looks like from the outside. But while you're riding in your car, you can see other cars. Some are minivans. Some are taxi cabs. Some are pickup trucks. Some are buses. Some are SUVs. You see all these other assorted kinds of cars. And you know that they are different because they all move relative to the background scenery. And the background scenery is the far distant, further away things in the cosmos. So you start examining what you can from within your vehicle, and you start looking at size and shape and say, well, I can't be in a bus because my galaxy is not as big as a bus. Or my car is not as big as a bus. I can't be in an SUV because it's not shaped that way on the inside. And slowly, by process of observing and elimination, you start figuring out that your vehicle must be similar to maybe this one. That's how we will operate in determining the shape of the spiral arms in our galaxy. One of the other things that's incredibly useful to astronomers is called the 21 centimeter line in the element hydrogen. Hydrogen, as you know, is the most abundant element in the entire universe. And when hydrogen atoms get excited and electrons jump to a higher energy level and then they fall back down, they have a tendency to emit a radio wave that has a wavelength of about 21 centimeters. That's why it's called the 21 centimeter line of hydrogen. Why is this important? Hydrogen is everywhere in the cosmos, and this particular radio wave is not blocked by dust. Why do we care? The center of the Milky Way galaxy is absolutely lousy with dust, and you can't see through dust. It's like seeing through solid matter. But radio waves can come through, and by examining this particular set of radio waves, we can get some good pictures of what's going on beyond the field of visible light waves. Now, interstellar space, the space between stars, has a very low density of about one hydrogen atom per cubic centimeter of space. Now, 1 cubic centimeter is about the size of a bouillon cube or a sugar cube. And in that much space between galaxies and stars, there's about 1 hydrogen atom in each one of those cubic centimeters. Interstellar space is not perfectly empty. It's really close to being empty, but not quite. This interstellar space is what is mostly out there, and it doesn't glow. It's not bright enough to glow. It doesn't have enough density. Astronomers look at different areas of space and have divided them into H1 and H2 regions. An H1 region is one that contains hydrogen atoms that are more dense. These we can see in the 21 centimeter line of hydrogen, but were not visible in visible light. These are areas that contain lots and lots of dust. And there's a lot of dust in nebula, and there's a lot of dusts in galaxies. H2 regions are regions that have so much kinetic energy, so much heat, that the hydrogen gas itself glows like we looked at spectral lights early on in the semester. And if you see light that is glowing, this is a high energy emission nebula area of a galaxy, and that is a different structure. So by mapping all of these different regions, that helps us put together the overall picture of what our galaxy is going to look like. I love this combination of pictures. Each one of these is a picture of the Milky Way galaxy. Now, how in the heck do you get pictures of the Milky Way galaxy that look like this? Well, let's go forward, or let's go back a little bit. Nope, I'm going to go forward because I need a little room to write. Here's how this works. We believe that we are in a spiral arm galaxy. That's what the evidence suggests, and we are about 2/3 of the way out on one of these arms. Now, because we live on part of one of these arms, we can't get a view from the top looking down. We can't do that. We can't just see that far because we don't have a probe or something up there. So the only thing we can do is when we look at the galaxy, we look this way at the galaxy. And so we see a thin, skinny slice of galaxy. It's sort of like if you took a picture of the galaxy and you folded it, so all you could see was this much of it, and we were sitting here, and we can look towards the center, and we can look towards the outside edge. And so very often when you see pictures of our Milky Way galaxy, they're going to look like long, skinny pictures because we're taking them looking towards the central bulge from our position out on one of the arms. So from our position on one of the arms, this is the very dense core of the Milky Way. A lot of heat, a lot of energy. These are spiral arms as we're looking at them sideways. So if you take a picture of one of these spiral arms and you're looking at just the edge-on view of them, that's what we're seeing in these pictures. And by reconstructing these images from lots of different wavelengths, visible and radio and infrared and ultraviolet, This is how astronomers are getting a picture of what our galaxy actually looks like. Here's a beautiful picture down here, this black one with lots of dots in it, where there are these stars exist in arms, and the areas between the arms, those are the regions where there is just dust, or interstellar space. Here's another picture. This is the central bulge of the Milky Way. These are interstellar space, and then there's an arm and an arm and an arm and an arm and an arm, and the areas between, that's interstellar space. By putting a lot of evidence together, that's how we're picking out the shape. Now, as astronomers were looking at this spiral shape, they were finding different kinds of stars existed in different regions. So young stars have been found to exist in the arms. And if you start looking at the arms of galaxies, we determined that the central core has got older stars. And you and I know they're older because look at that color in that central core. It is redder, it's oranger, and that is an indicator of older stars. Out on the spiral arms, you've got more pink. Pink is hydrogen gas, and that is also where you're going to find some bright blue stars. And those are those O and B young hot stars. They exist in the spiral arms of our neighboring galaxies, and we assume we're in a pretty typical galaxy. So when we see lots of these bright arms, we assume that we are in that situation as well. The arms of our galaxy have been given names, and they are given names depending upon what constellation is you have to look, or what portion of the sky you look into to see these various arms. So if this is the center of the Milky Way galaxy, if you look towards Perseus, there is the Perseus arm that we see. If you look towards Orion, there is the Orion arm, and this is our representation of where our location is. We are on the Orion arm of the Milky Way galaxy. You look towards Perseus, you see an arm. If you look towards Crux Scrutum, which happen to be constellations in the southern hemisphere, you see those arms. Carina Sagittarius, that is the name for the constellations for this arm. So there are multiple arms of the Milky Way galaxy. Each one has a name. The central bar, we'll talk more about that later, the Skype arm, the Norma arm, the Crux Scrutum arm, the Carina Sagittarius, the Orion arm, the Perseus, the outer arm, and then because we found another outer arm, the new outer arm. Our galaxy rotates, and it rotates once about every 250 million years. And it kind of is like a rolled up little sandwich or a little fruit roll up. And its kind of pinwheel shape comes from this rotational motion. This is just, again, not our galaxy, but another one that if ours looked like this, we would be on Sol, means us, the sun, and we are out here on the Orion arm. Those of you who are Star Trek fans, okay, Star Trek fans, this is true, not science, but kind of interesting. The sun is right on the border between the alpha and the beta quadrant here on the Orion arm. If you are a big Star Trek fan, some Star Trek movies, etc., have the Borg Collective. They are over on the Norma arm and the Scrutum Centaurus arm in the delta quadrant. The Dominion, another section of Star Trek, is over in the gamma quadrant of the Milky Way. And then the Klingons are over in the beta quadrant, and then the United Federation of Planets, home, Earth's the sun. This is right between those two. Those of you who are big Star Wars fans, that's in a galaxy far, far away. So yeah, we can't make sense out of that. Not with our galaxy anyhow. Here's another picture of the arms of our galaxy. Again, based on Star Trek. Trekkies are nerds, so they kind of have some interplay of real science with fake stuff. the Sun, United Federation of Planets, the Orion Arm, and then this is just not a bad kind of illustration of the different arms around our galaxy. Okay, we have talked about that flat plate, that galactic disk, the halo, the globular clusters around it, and now we're going to spend a lot more time in the next video talking about the halo itself. See you next time.